phase. Okay, and then the order of events is very important.
That's all we're further about.
There we go. You're ready. That's you stop at this one. Good. You have not. You said that from here there's a lot to talk about, and you ended 2 minutes early.
That's my plan. Makes sense, right?
Yeah. Just a sec. All right. Okay, I have your attention. I can't whistle. I don't know how to whistle. Okay, groups, you're doing great, but pick up the competition. There's one group that got +2 weeks in a row. So you gotta beat them.
They're already far enough ahead.
What's that? They're good, but okay. You can be good too. All right, another announcement about the quiz. On Monday, a couple of you asked if we do not include the mass spec for the quiz on Monday. You want to study it or you want to keep it for the midterm? All right, so through chromatography, including GC. That would be the material to study for the quiz. If you have your lab notebook that I have to still look at, give it to me now. I will be sitting in the back while Gary is lecturing. I'll be looking at your lab notebooks. Okay, all yours.
Okay, well, I guess this is about where we got last time. And so moving on to how we interface mass spectrometry with HPLC. And that is really one of the most active areas of research, most active areas of development in terms of methodology, analytical methodology. And mainly because liquid chromatography has poor resolution. It doesn't compare at all to gas chromatography. So we need to depend much more upon that detector to be specific. So instead of separating things completely, well, partial separation, a little bit of separation is adequate. So it's really turned HPLC into a much more powerful, a much more useful technique than it was in the past. Being able to have a detector that has the kind of capabilities that mass spec do. There is a problem, of course, that the carrier flow, the mobile phase, is a liquid, and it will end up having a volume, once it gets inside of a vacuum, of up to 1,000 times that of capillary GC. And so one of the challenges that we run into is how do we deal with that much solvent? We have to have ways to get rid of it, or to completely destroy the vacuum. We wouldn't have any spectra to measure. So there's been a good deal of creativity in terms of the inlet systems and how they manage them. These are some of the more common: atmospheric pressure, chemical ionization, electrospray, thermospray, particle beam interfaces. And I guess we end up using the first two that are underlined fairly commonly. The other two are a little less commonly used. So this, if it decides to move, let's try that way. There we go. So this is electrospray. So electrospray ionization, ESI. Very common, you'll see HPL or LCMS, or I'll get it right, LCESIMS, electrospray ionization mass spectrometry. There we go. And so this is basically what you're talking about. And so you will have the effluent coming from your LC that comes out into the system. So this is under a fair amount of vacuum already. So you're putting liquid into a vacuum. There's a needle there that has about 4,000 volts on it. So right about here, you get a really high electrical potential to the liquid. And so when it sprays, you're doing your ionization. So this would be, let's say, a droplet that's coming off here, one of these droplets. So it would have a great deal of ionization, charged droplet. Since this is in a vacuum, your solvent's going to evaporate. So your solvent's going to be will be lost from this droplet as it dries. So we're losing our solvent out. So we're concentrating around our analyte. So we're getting rid of more solvent in this vacuum region here. And hopefully by the time you get into the point where it enters the mass spectrometer, you're left primarily with positive charges because you've got the ability to drag these positive charges out. So your negative charges really aren't attracted down this tube, only your positive charges. So negative charges, less solvent tends to be drawn out of this section to give you then just this concentrated beam of material from your LC column. Atmospheric pressure chemical ionization is actually a somewhat similar system. I'm going to show you an application of this a little bit later on. But here's your capillary tube, and this can come from the air. It can be in a balloon riding up in the sky, monitoring pollution. It can be almost any place. So you're going to be drawing in actually an atmosphere of some kind. Then it comes drawn into the system. There's now a corona discharge needle here that's again a few thousand volts. And so you put an electrical charge again on anything that's coming through this inlet system. And from that, it works much the same. Your ions then are drawn out by a negative charge and simply enter into the second vacuum region and into the mass spectrometer. So any air that you're drawing in here tends to get drawn out that way. Any positive ions that are formed get sucked into this pathway. So again, getting rid of, I hesitate to call the atmosphere that you're drawing in a solvent, but I suppose air is a solvent because that's got your analytes in it. So an interesting way to go. There's different ways of presenting mass spectra when you're feeding it from liquid chromatograph, or for that matter, from a gas chromatograph. What happens in the way the system works, it will draw something that looks like a gas chromatogram or an LC. And basically, it's pretty much similar to that. And so what it does is, when you get an analyte coming in, you form a lot of ions. And your mass spectra samples that. So it samples the number of ions. And so it's saying, okay, I got a high ion concentration here, I go up, okay, the ion concentration is going down. So draw something that looks like a chromatogram in a gas chromatograph, or like I say, regular LC, but it is based on the number of ions formed. That's its detector. And oftentimes you can see a presentation. So there'll be a mass spectrum taken here, and here's, now this is the mass spectrum that we saw, we've seen before. And they can also then present them sequentially, so you can see how the composition of that peak may change or stay the same as we go up, down component, one component after another. And so that's your detector basically is an ion detector, and that's all that it's doing. For quantitative analysis, you, again, by mass spectrometry, you get to do something that you can't do by any other detector. And that's using stable isotopes as your internal standard. When you choose an internal standard to use in your method, you always pick a compound that's closely related to the analyte you want to measure. You want your internal standard to behave exactly like your analytes. If you extract, if you evaporate, however you choose to prepare your sample. And so your internal standards are very important. And like I say, you want it to be just as close as possible to the characteristics of the compounds you're analyzing. And there's really nothing better than just a stable isotope of your compound. I may be interested in benzaldehyde. I like cherry flavor. Benzaldehyde creates cherry flavor. Okay. But if I want to measure it, what's my best standard? I could put a carbon 14, well, carbon 13, I'm sorry. I can't do carbon 14, that's radioactive. That would be a problem. Let's do carbon with 13. And then, so I've got one that's enriched in carbon 13. I have one that doesn't have carbon 13 in it, in a special amount. And I can simply, by mass spectrometry, I can get a peak for the benzaldehyde with no carbon 13. I can get a peak for with carbon 13. So I've got that compound. My compound is my internal standard. Life doesn't get any better than that. We've got an example coming up using nitrogen 15. So you spike your sample with the surrogate, do MS, multiple ions, generate ions, planogram, plot ions of interest. You can integrate them by proportion. If you know exactly how much internal standard you have, based on the area of your peaks of your surrogate sample and your compound of interest, you can say exactly how much compound you have. This is one where there's a nitrogen 15. So example, what is it? 5-fluorouracil in blood plasma. So this may be your sample. There's other peaks in here. There's your compound up here that you want to measure. If you would go ahead and make that material with with nitrogen 15, this is going to have a mass 2 units bigger. So the standard now, the 5-fluorouracil with nitrogen 15 is going to be 160. So I set my mass spectrometer to take my normal sample, so the mass of 158. So this is a peak of mass 150 only. Here's my sample, same compound, except like I say, it's got nitrogen 15 in it, and I get this peak. So again, by proportion, you can calculate the amount very nicely. So again, mass spectrometry gives you tremendously accurate quantitation, much better than you can find in any other technique, due to that ability to have an internal standard. It's absolutely perfect for what you want to measure. The idea of GC peaks, I probably started off at some point with that. It's really important to know what you're measuring. It's important if there's a peak and it comes exactly, it's exactly where the compound of interest, that doesn't mean it's the compound of interest. You need some way to guarantee that that peak you're measuring is what you think it is. And again, there's no better method, let's put it that way, of going ahead and ensuring that what you're measuring is in fact what you think it is. The mass spec gives you that kind of identification. You can do MS. So what you're doing is you're having one mass spectrometer, and that's interfaced then with a second mass spectrometer. So there ends up just being one continuous region where you form ions here, you separate ions there, and then you select a certain ion and you do mass spec on that. And so you can then not only get a mass spectrum of a whole molecule, but you can then check every fragment, every piece of that molecule is what you think it is. And so that gives you tremendous, again, resolution power and identification power. So it's really another neat technique, and that's used fairly commonly in the industry, because if you get a fragment and say it's mass 58, well, that mass 58, that could be a number of different things that you can put together. What can you put together that equals 58? And so just seeing a 58 doesn't mean necessarily what it is. But if you take a mass spectra of that 58 and blow it into pieces, then you can see what that is. So again, ability to quantify and identify accurately is tremendously powerful. Here's an example of a triple quad. So it's basically MSMs, mass spectrometry. So you're getting your sample put in here. There's the first MS that comes here. There's where you separate and say, okay, I want to look at certain fragments of a compound. I want a spectra of the compound spectrum. And so we end up having two mass specs interface. then we're going to go through some applications. It'll be a little bit heavy about the things, how we use it. So the examples will be to some extent from our laboratory or our use. Flavor protein reactions, that's a primary area of interest for me today. We're on protein, more protein in our diets. We're putting proteins in foods. We may be fortifying some beverage with protein, then we're also flavoring it and putting something else in it. So there's a lot of opportunities for flavors to react with proteins. They're extremely reactive materials. And so that's been a primary area of interest lately. I'll give you an example of how to use it there. Aromal release in the mouth. And that's kind of a strange one. Why do I care if an aroma is released in the mouth? Well, I'll give you, like I say, an example of this. But what you find is that foods differ in flavor depending upon the composition of that food. If you have a food and it's got a certain protein, fat, whatever, water level, and you change one of those factors, it might be twice as much protein, 2% more fat, whatever, it changes the flavor. Oh, really? How does it change the flavor? I put the same flavor in. Why isn't it the same? That's kind of what we're looking here. I know that flavor's there, I put it in, but I'm not perceiving it. Why aren't I perceiving it? And so the idea, is it given up when you eat? Or does it just go down your stomach and it's gone? So that's an area that we found interesting too. Identification of unknowns in foods, oh, that's a routine. Assurance of purity, that's a quality analysis. Quantification of analytes, adulteration. So there's, again, a lot of applications in the food business. And believe me, that's just a touching, a small example. So this is an example that we look at. So our model protein is beta-lactoglobulin. It's the major whey protein. So beta-lactoglobulin, if I put this into an LCMS, I do ESI, MS, electrospray ionization, mass spectrometry. This is the profile I get. This is the ions that I see. I get a very large peak at 18,276. That's beta-lactoglobulin. So I can actually measure the mass. I can measure my beta-lactoglobulin peak, how much is there. There's some other fragments that come along here, a little bit of addition onto our protein. So these are covalently bonded. There can be some oxidation products, some minor changes. And so you see a little bit more here. But by far, our major component is beta-lactoglobulin with no chemical modification in nature. If we go over here, so the mass spectrometer is scanning through higher and higher masses, I see another mass of 18,600. That's 324 AMUs bigger than the pure protein. What's that? It's the Maillard reaction. What's there? Lactose. Lactose undergoes a Maillard reaction with protein. And so the machine is also measuring now my Maillard reaction. So I've got a shift space formation. That's one lactose, so that's this paired protein plus one lactose, and this is with a second lactose. So again, I have the ability to measure what adds on to my protein, what's chemically reacted with my protein. I can measure sugars, I can measure anything that's added on to my protein. So this is an example now. This is exactly what you saw before. This is my pure protein. So here plus one sugar plus two sugars. And here's why I took benzaldehyde, my cherry flavor, yep, in only 10 minutes. So I added my flavor to my protein solution. 10 minutes later, I took the sample off, checked it in the mass spectrometer, said, did anything happen? And so yep, here's this, just like it should be. But I've got a new peak here, 18,364. That's the mass of benzaldehyde. I just covalently bonded benzaldehyde to that protein. Guess what? I lost that benzaldehyde. It doesn't taste, it doesn't smell, it doesn't contribute to your product anymore. And not only, of course, does it react with this free beta-lactoglobulin, but also with the ones that have sugar added onto them, too small to see out here. So I got a way, like I say, of measuring what happens to my protein and what happens to my flavor. I got percent protein, I got parts per million flavor. So I really get concerned about that parts per million, where it's gone. This is 6 hours later. So this is again room temperature. What do we have now? We don't have this little peak down here as we did see before, but we've got a peak that's almost as big as almost every molecule. Well, let's say 50%. 50% of molecules go here, 50% is now added on benzaldehyde, and so on down the line. I couldn't do this by any other technique. There's no other methodology that gives me this kind of information. And that gives us ability to study different proteins. Are they chemically reactive? Pea protein more reactive than soy? How does beta-lactoglobulin? By the way, what happened to my flavor? I had put my flavor in there and it's disappearing. Actually, I pasteurized it and it completely disappeared. So it's explaining what's happening to my food system. So we have some opportunity of intervening in this whole system. This is another project, determining the effect of bulk sweetener with aspartame on a rodent release profile. And this kind of came about from the idea that beverages, again, I don't know, I'm a Diet Coke person. I like the flavor of Diet Coke. I don't really care for the flavor of regular Coke. It's different to me. And it's not the one I prefer. I think it was 50-50 or something like that. Many people prefer sugar sweetened. But why is it different? Why is there chemical difference, a perceived difference between the two beverages? So in this particular study, what we did is we made a beverage. We added no sweetener. We added aspartame sweetener to another one, so equally sweet ratio. Oops, and this is equally sweet between sucrose and aspartame. And then that was, so the beverage base was made, it was diluted. And then I'm kind of curious, well, why are these different? Why don't they? Aren't they perceived the same? And this is a fellow from the UK that's been in our laboratory on occasion. And what's he doing? He's sipping on a beverage. That's sipping here. He's got a tube up his nose, doesn't go very far up there. And so this is actually drawing his exhaled breath. Every time he exhales, this tube samples into what? A mass spectrometer. So I can get a good look at what he's exhaling, because that's when you smell something. You don't smell when you put it in your mouth, that you swallow. Every time you swallow, you exhale. Check it out, you'll exhale. That's called the swallow breath. And that breath comes right back where that beverage went, down your throat. So it comes back out that way. And so what he's exhaling after swallowing represents the flavor that he was given up at the olfactory region. So it's really a fascinating result. Now, this I won't spend much time with, but this is.
Is that a humidity port, or did they have to change that? Do you think they changed that port, or is that
the nose port?
Yeah.
Yeah, so.
They have their own that they bring from home?
They could. And so this is what it normally looks like. The major volatile we exhale from our body is acetone. Not because you've been working in the lab all day. It's the metabolic byproduct of your life. How's that? And so the major chemical you've got in your breath is acetone. And so here's the machine. It's monitoring his breath. Okay, he exhales. We got something to measure. He's inhaling. When he inhales, there's nothing going past the membrane. So exhale, inhale, exhale, inhale. Right about here, he took this up in the juice and swallowed it. Okay. Now I'm looking at different flavor compounds that are present in that juice. I know what they are, and I have my mass spec to measure this flavor compound, that one, that one, that one, so on down the line. So what do we find? What we call the swallow breath. We get, oh, we get their flavor compound. Oh, a little bit there, a little bit there. Oh, it really goes away pretty quickly. The same here. So here's 1, 2, 3, 4. And then it hits you and then it goes away, which fascinates me because there's a lingering sensation. It isn't like the swallow is gone, but yet you aren't given any more stimulus. So it is gone, but your brain keeps thinking, oh, it's still there. But some of other flavor compounds, what happened? They got a spike, but then they continue for a long time. Long time meaning 2.6 minutes on the scale. So it's really interesting. I couldn't do this. I couldn't study behavior, of flavor compounds, your perception, without this technique. There's no other way to do it. Purity, GC peaks, we're not interested in that. We saw that. Identification, the idea of looking for pesticides, contaminants, undesirable odorants. And it's really tremendous. Power, resolution, and identification. This is another application that we have in our lab. I'm interested in encapsulating flavors. Flavors are fragile. They evaporate, they oxidize, they go away. And so what do? We tend to encapsulate them. We put them in particles. They're small particles, spray-dried particles. They're maybe 50 microns in size. But I put my flavor into this matrix, into the slurry, and I spray-dried. So I got my flavor trapped inside of the matrix. But it's one of the things I have a question about is this is a droplet of flavor inside this powder particle. I've basically broken that flavor particle in half. So I got this 50 micron powder particle, split it down the middle, and I start doing mass spectrometry of the surface. And this is the interface between the flavor particle and the water. And so it gives me the power to look and see, what is this interface? This interface protects my particle from oxygen. How can I change that? How is it changed? Where is it? And again, I'm using it as an image. It's not, a number. It's not a spectrum. It's converted into an image so you can see things. Certainly, it's a growing technique in the food field. Back at one time, mass spectrometry was something available, obviously, to only very few people. Then the cost has come down, and so it's become more common. You'll find gas chromatography, liquid chromatography, mass spectrometry joined to them more and more in laboratories because they are so functional. They're so helpful in terms of identification, making sure you measure what you think you are. And again, they are easy to operate. Easy to operate, scary, because anybody can operate. Anybody can go in and push the button. But there's more to it. Like I've said before, you need to be able to understand what you did, why you did it, and how to interpret it. And that's kind of a trap in a sense. You get data, but is it good data? That's up to you to decide what's good and what isn't. So easy to operate, more difficult to understand. So again, do your homework. Computerized databases and data handling. And again, that's a blessing. You don't necessarily believe what it tells you. You validate every one of them. Computer, as I said, it does what you tell it. It doesn't do what you want necessarily. It does what you tell it to do. And it does it well, but okay. But advances in instrumentation, it's moved out of just a research function into just an everyday function these days. So I'm really impressed with what's been done, where this methodology has gone. It's just exceedingly valuable. It makes your other tools much more valuable as well. So that's a sampling of MS. I wonder if your professor wants you to go home at this point, or if she wants you. Here's what we're asking.
I was going to go over with the lab. All right, I'll take what you got.
I'm done. That's how I know. So I'm going to go away. Nice to see you all. We'll catch you someplace else, I hope. Bye, Inspector.
Why are you using?
Because I'm done.
No, I haven't.
I lost my keys. I gotta go find them. Honestly.
Figure out it.
I also. Take care.
Okay. Oh my gosh, he's gonna come back for it. All right, don't
You want
go.
to run it to him?
No, you stay. Let him come back.
Okay. I think so. Well, what if he just rides without help?
It's funny if he comes back.
Oh, you came back now.
Yeah. Okay. I hope I don't forget it too. I'm just gonna. All right. So I know that there was confusion about internal and external standards last time. So I asked Regina, because she's wonderful at presenting stuff, to put together some 2 slides to reinforce the learning. Okay. I want to make sure you understand this concept. I'm not going to start HPLC lecture. Don't worry, we'll start it on Monday after the quiz. So I just want to go make sure that you understand this concept. You can take pictures, yes. So internal versus external standards. So internal standards is a substance or a compound with known concentration. So you have a known concentration that you add to every sample and every external standard at the same concentration. So what is the criteria for internal standard is to be structurally similar to your compounds of interest. By being structurally similar, it will elute during your analysis time, but it will not co-elute with any of your compounds. This is a must, otherwise it's going to be useless. Okay, purpose. Why do we add an internal standard? To correct for variability or any experimental error during sample preparation that might cause losses. Either sample preparation or sample injection, especially with the GC, sometimes the volume you inject is not consistent, so this can correct for that. Now, your external standard is you're measuring glucose in your sample, you want to get a standard glucose that you don't add to your sample. That's why it's called external. So you prepare different concentrations of your sample, of your standard, and you would run them like we did for the caffeine lab. You run them separately from your sample, and then you get an area under the curve, and you have your concentration. You can plot a standard curve. That standard curve is the external standard curve. So the criteria is basically have the exact same compound that you are looking for to determine and to quantitate. And that's it, used for determination, identification, and quantification. Why do we do that? We generate a calibration curve, either for identification we do it, or for quantification where you have to determine a standard curve so that you can get the concentration with or without an internal standard. You don't have to always have an internal standard for quantification. So you can run your external standard with or without an internal standard. So in a lab task, you have a molasses sample and you want to determine your sucrose, glucose, and fructose naturally occurring in your molasses. So your internal standard, you choose another sugar, another disaccharide, lactose that is not present in your sample. It's a milk, a dairy sugar. So you use that as an internal standard. It's gonna not co-elute with any of your compounds. It's gonna come out during the analysis time, and it's not, and it's structurally similar. Okay. And then your external standards are the exact compounds you're looking for: sucrose, fructose, glucose. We're going to use that to generate standard curve, separate standard curve for each of them, to quantify each of the compounds in your sample. Welcome back. I knew you were coming.
I'm leaving. I'm leaving.
No, you can stay. That's God's wants you to stay.
She's going to get more than that.
Okay. So that's that. This isn't that wonderful? Yes. I can't hear you. Have to scream.
Here's my question. The act, for example, that somehow want to apply heating, mixing, or whatever. Should we add somehow before that?
Yes, at the beginning of anything that you do, like if you are doing any sample prep, any heating, any transfer, anything has to be at the beginning added.
Okay, you're going to add equal amount to the estimate.
To the sample.
Estimate solution doesn't go.
No, that's why we take the ratio. The ratio corrects for every, so
step.
every step, and then you have your internal scan in every chromatogram, you take the ratio. So you correct for difference. So the ratio is the standard internal and external, and then the ratio within your sample. So you don't take the ratio to the internal standard that was done alone. Take the standard in that will talk. That's the stuff. It will talk. Okay, so this is wonderful illustration here. Brigida gave the lactose internal standard this red drop color, and you added at the same concentration. So the same drop is added to all of your external standards in this case. Sucrose, glucose, fructose, you prepare them at different concentrations, and you add the same amount of lactose to all of them. So the color coded, don't you like that? So organized. Okay. And then you run your standards. You run glucose standard, fructose standard, lactose standard, sorry, not lactose, sucrose standard. And in each of these standards, you have the same lactose amount, same area, but different responses. Even if it's the same concentration, you have different responses of the different compounds. So you take the area here, and that area over this area is what you would plot. So if we're doing glucose, the green, the area of glucose over the area of lactose is what you plot here at the concentration or the first concentration of glucose. The second concentration, the third, the fourth, the fifth. You have your calibration curve. It doesn't have to have, you don't have to have a figure with 3 calibration curves. They can be separate, but you would have a calibration curve for each of these and equation of the line for each of these. Your y-axis is the ratio of the area in each concentration, the ratio of the area at each concentration. And the axis is your concentration of the standard. So you get an equation of the line for each of the lines. Now your y, okay? So this is your sample. So the sample has all 3 sugars and you have your lactose. So for each sample that you run, you'll get an area for each of your compounds of interest and an area for lactose. Your y is the area of your glucose over the area of lactose. The area of fructose over the area of lactose, the area of sucrose over the area of lactose, that would be your y. Then you can determine the concentration. Okay? Questions? Ellie?
you only make constant calibration curve when you use an internal and an external?
No, you did calibration curve for caffeine without an internal standard. So you can do calibration without an internal standard. You can do sample analysis without an internal standard. But when you have a sample preparation that is tedious, heating, transferring, centrifuging, blah, your internal standard is going through all of these steps. So anything that is lost during these steps, the internal standard will also be lost at the same proportion. That's why we take the proportion of the area. Okay. Not always you need to have a quantification, right? Sometimes you just need identification. In this case, internal standard is not really that important. When you want to do quantification and when you know that your sample prep is going to be tedious, you might have losses, then it's great to have an internal standard. But you can do quantification without an internal standard. Does it make sense? You can ask more questions. I'm happy to repeat. Yes, Michael.
So in GC Lab, I'm not quite understanding why it's only semi-quantitative when we do have an external standard. Why can't we quantitate that?
We can, but the only thing we didn't do is we didn't run our external standards at different concentrations. You only injected the external standards mixed together at one concentration. And you use this data to identify your different fatty acids. And the way you determine fatty acid composition is by doing the ratio of the areas to each other. We call that semi-quantitative because we didn't do a calibration curve. You didn't run your external standards at different concentrations. And so that when you don't do that, you don't account for the detector response. And I don't know if it was you, Michael, or somebody else, I drew it the other day. What I mean by the detector response. Let's say I have compound X, compound Y, they have equal concentration, the same concentration in my sample. When I run the chromatogram, I might see this, I might see that. Same concentration. And here, let's say FID, so it's, what is it? Conductivity. Yeah, is it conductivity? No, that was thermal conductivity. It's the change in current, right? Change in current is what you measure because you have a potential and you have ions. So change in current. Okay, so every compound has a different set of ions that can be formed. Okay, the ions that are formed from this compound and this compound, they can impact the current differently. So even at their same concentration, their impact on the current is different. So if you don't run a standard curve, you're not accounting for the response factor of the detector. So that's why it's semi-quantitative. We didn't run a standard curve, we just compared areas, relative areas. And that's how you got the composition of fatty acid based on relative areas. It's not the exact concentration. You want to get the exact concentration, then you need standard curve. So your values are not going to be exactly the same as the SDA values when you compare your percentage composition, but they're going to be very close because you didn't do calculation. Any other questions? Yes.
So
I can't hear you, Samira.
if this internal is standard, you're going to have this conclusion that the ratio of the areas with this background and the standard solution changed in this way.
Yeah.
So the glucose or sucrose are going to change in this ratio. So we use that ratio that we have this loss with
But in every sample, you might have different loss happening. So when you're running, you'll have molasses, you're doing replication. Yeah. Or you're looking at different sources of molasses. Because there is experimental error that is going to be different in every sample. So that's why within each sample, you need to correct for that. Yes. Make sense? Yeah. Are you ready to go home? Mm-hmm. Or you have classes still? All right, 5 minutes extra. You can leave. Thank you. Hi. Hi. Yeah, you can take this in the back. Don't forget to take your lab notebooks in the back.